So we have the classical Lagrangian field theory. Now classical Newtonian field theory. So first of all, in any classical Hamiltonian field theory, just as in the Lagrangian case, we have to fix a space-time category. And then such theory consists of certain data which satisfy certain properties. So data for, I'll abbreviate CHF. So when we have a space-time category, let's assume that it's d-dimensional, objects and -1 dimensional, morphisms d-dimensional, d-1 d-dimensional. So to each object we assign a symplectic manifold. And then to each d-dimensional space-time we assign a Lagrangian submanifold in this, oh I'm sorry, this is md-1 and the t-1 dimensional boundary of M. So roughly speaking, this is what the data. One can relax these conditions. One can see what happens if L is isotropic or coisotropic. Let's not go into this. So let's just take this as a definition. But then this data should satisfy certain axioms. And the axioms are the following. So I wouldn't forget any. If it's an empty space, the symplectic manifold is just 0. Then if we have disjoint union of two d-dimensional manifolds, the corresponding symplectic space is the Cartesian product. Then if we have the disjoint union of two d-dimensional manifolds, the corresponding Lagrangian subspace is the subspace in the boundary of this disjoint union, and it's the Cartesian product of Lagrangian subspaces in this symplectic space. So then the if we will change the orientation in the d-dimensional manifold, the corresponding symplectic manifold changes the symplectic form. So then if we have a mapping from N1 to N2, so it orientation preserving isomorphism. So then it leads to the symplectomorphism of n's. And then the last axiom is related to the gluing. And in the most general way it can be said like this. So suppose we have a manifold M with the boundary components which are symbolically wrote like this: dm1, dm2, dm prime. And let F be the orientation reversing orientation preserving map from one component of the boundary to the other. So then we can clue Fm. So it's something like this. This is F. This is the orientation of the boundary. So it's M, and then the result of the gluing. So the equivalence induced by F. So then, as part of the data, we have LM1. I'm sorry, we have LM in M and LMF SDM SDMF, but DMF is just DM prime. And this is S of DM1, DM2, DM prime. And according to one of these axioms, it's just a product of corresponding symplectic manifolds. So it's part of the data. We have two Lagrangian submanifolds. And then the axiom is how they are related with respect to this gluing. And they should be related in the following way. LMF is equal to the set of points dm prime such that there exists y in S dm1 such that the triple y S of the gluing map applied to y and x belongs to L. So the data of the theory gives us these two manifolds, but then the axiom is that these manifolds should be obtained from, should be the result of this, should be equal to this submanifold. So I should say that actually I learned this piece from Volodya, this Hamiltonian piece, and I don't know why he learned it.
Many sources.
And of
of course, this may not result in the Lagrangian submanifold.
No, this is a very rough draft of what it should be.
Well, it's an axial, so
It may not hold, it may not.
a priori not.
So it means, in particular, one cannot always do the dual.
Certainly, here it isn't an axial, so if you cannot, it's not there.
Yeah. Well, the reason why I ask is because there is this Lagrangian cobordism category by
Right.
by
Of course,
Woodward
you can
and
extend.
who was the other one? Verheim, yes. Where they somehow they kind of somehow admit that you can't really do this in general and get a Lagrangian subspace, but then they sort of do a virtual construction where you do this, just assume kind of they were
Well,
there.
the simplest version.
That's what I mean, that it's a rough draft, but then that's the idea. And then, of course, in reality,
Right.
you cannot do it, but you can do some variations of this.
No, there are some cases that you can do that. It's not
Right. Sometimes you can do it, but some other
Yeah.
times this simply doesn't work. Yeah.
Okay, so that's the idea. That's the idea of what it should be. The question is when it works and when it doesn't.
So a certain transversality condition.
Exactly.
Some
Yeah.
diagonals will be transversal to the graph
Exactly.
of
Then it works, and if not, you
So now let's look at examples. Let's start with the classical mechanics. So in this case, so remember that we have this smooth manifold N that is called where the coordinates were the positions of the system. So this is the configuration space. That's the standard name in mechanics. The important role was played by the tangent space. That's where the Lagrangian of the theory is defined. So in our example, N was Riemannian, and L had this particularly simple form minus V of Q. So, in general, yes. So now let's see what did we have on N. We have the classical solution. So classical solutions or solutions to the Euler-Lagrange equations. Then, of course, you can lift them to the tangent space simply by mapping gamma to the path gamma dot t, gamma t. Gamma dot t is a natural tangent vector at any point t. So but then there is a natural passage. So once you have a function L on the tangent space, so if L is good, I'll say environment of what it means, you can pass to the cotangent space, and this is called Legendre transform. And we can have a general discussion of the Legendre transform, but that will take time from everything else. So fortunately in our example this is very simple. So this isomorphism via the Legendre transform is the same as by the metric So the image of the path gamma in the cotangent space is this one, and that's a flow line of the Hamiltonian vector field VH, which is omega inverse dH, and here H is the Legendre transform of L. So it's PXC minus LCQ. Omega is the standard form, symplectic form on the cotangent bundle. In local coordinates, it's sum over I dpi dqi, where qi are local coordinates on n, and p sub I are natural induced coordinates on the cotangent spaces. So, and pi pq. So
this is just D of the canonical one form.
yeah. Where theta is a canonical one form on the cotangent bundle. Okay, so again, fortunately in our case, the Legendre transform is very simple to find. It's equal to this plus V of Q, where this is the scalar product on the cotangent spaces induced by the metric on M. So this scalar product is on tangent spaces, and this is on the cotangent spaces. Okay. So this is the Hamiltonian formulation of the Lagrangian mechanics, but this is not in the form of the Hamiltonian classical field theory yet. So now let's formulate. So this is the standard thing that's in all textbooks. Once you have a Lagrangian, you have the sort of classical trajectories defined by the minimal action principle, or rather extremal action principle, and then you have trajectories on the tangent space. Through the Legendre transform, you can pass to the cotangent space, and then on the cotangent space you have the Hamiltonian, which is the Legendre transform of L, and its Hamiltonian vector fields are exactly the images of the solutions to the Euler-Lagrange equations. So in this way you connect solutions to the Euler-Lagrange equation to Hamiltonian vector fields on the cotangent space. So on T star M we have the flow lines of VH, and they project to solutions to the Euler-Lagrange equations for L given by the inverse Legendre to H. Okay, so now let's formulate this in terms of the Hamiltonian field theory in the way how I explained before. So space-time category is the same as in the Lagrangian case. Objects are points, morphisms are segments of the real line. So this is our space-time M. So now we have to assign a Lagrangian. So first we have to say what is the symplectic manifold corresponding to the boundary of M. Boundary of M consists of 2 points. The target point and the initial point of the interval is oriented. So this is equal to T star N with omega cross T star N with minus omega, where omega is this canonical symplectic structure on the quantization model. And then L, M, and remember that M is the interval T1, T2. This is simply the space of all so this is the space of all points P1, Q1, P2, Q2. In the product in the Cartesian product of 2 tension bundles, such that there is a flow generated by H, flow of this vector field VH, connecting P1, Q1 and P2, Q2 in time T2 minus T1. So these are all pairs of points P1, Q1, P2, Q2, such that if you start here at time T1, you will arrive here at the time T2. And this is a flow line of the Hamiltonian vector field generated by the Hamiltonian, which is the Legendre transform of the Lagrangian, generated by this Hamiltonian. Is it clear? So now we have to check the axioms. So the only thing we have to... So objects are points, so if you have n points, you simply have n copies of the T star n in the product. And so the only axiom really that needs to be checked is this composition axiom. And that's the that's the relation between L. So now M is really T1, T2, but you can see that this Lagrangian submanifold really depends only on the difference T2 minus T1. So what we want to check is that T1, T3, L, T1, T2, L, T2, T3 satisfy the gluing maximum. Okay. This is the homework. So, all the so, in terms of the setting, in terms of what I wrote about this axiom, let's be very explicit what should be checked. So, we are gluing T1, T2 through the kind of tautological identification T2 and T2 here. So this is our gluing setting. And then, so in what was before, in what was written on that part of the blackboard, M is the product T1, T2 cross T2, T2, T3, and F is T1, T3. And so one has to check whether the corresponding Lagrangian subspaces, submanifolds, satisfy this gluing axiom. And so this is the second order, and then after this, it's the we have the Hamiltonian formulation of the second order classical mechanics as a Hamiltonian field theory, and you can see the important phenomenon here. The original field theory, the original Lagrangian field theory, was on N. The configuration space was N. The symplectic manifolds, now that we use in the Hamiltonian formulation, are cotangent bundles to N. So at this point, it's very productive to return to the discussion of boundary conditions. Because remember, boundary conditions we fixed sort of as Dirichlet boundary conditions. These were simply points on N. So now let's in Lagrangian formulation, the conditions were, so we had these Dirichlet boundary conditions, Q2, but now let's see what this means in Hamiltonian formulation. So when we fix a point on N, well, it fixes a submanifold, the cotangent bundle, the cotangent space at the point Q to N. And it's a submanifold and the cotangent bundle. And it's a Lagrangian submanifold. So it means that Dirichlet boundary conditions, they fix two Lagrangian submanifolds, L1 cotangent space to n at Q1, and L2 is the cotangent space to n at the point Q2. And now let's see why generically we should expect a discrete set of solutions to the Euler-Lagrange equations. So once we fix these boundary conditions, we have the product of these bundles is exactly our symplectic manifold. It doesn't matter whether something is a Lagrangian subspace in T star n with omega or T star n with minus omega. It is still Lagrangian. The restriction of the symplectic form to it is 0, so it doesn't matter with which sign you take it. So this is a Lagrangian subspace in our symplectic space S T1, T2. But we also have another Lagrangian subspace. That's the S T1, T2 collection of 2 points. But then we also have this submanifold, which describes the dynamics of the system. And so now it's clear that solutions to the Euler-Lagrange equations with these boundary conditions are intersection points of these two Lagrangian submanifolds. And so generically you expect them to be a discrete set. So you see, it's very, so that's the first observation. And second observation that T star Q n, these Lagrangian submanifolds that we used, these are fibers of the most natural Lagrangian fiber bundle that you can imagine for T star n. It's the projection to n. So you fix Q and then the cotangent directions is the fiber over Q. So you can see that the Hamiltonian formulation of the second order classical mechanics, it's very similar by nature to what we had in the first order classical mechanics. So again, if you want to glue the trajectories together, then you will have to vary over the intermediate coordinate Q. So you will have to vary the fibers of this fiber bundle. Okay, so any questions about the second order classical mechanics? It's really late.
You said a new term. You said second, you called it something different. Second order mechanics. Or you mean it's just because we're looking at the second order?
Second order
problems.
problems.
Okay.
The first order and second order is just it's the degree of the polynomial.
So, I guess it is.
So, if I have to finish earlier, tell me when people will be completely exhausted. So let's just go one more step. So let's have the first order. So this was the Hamiltonian setting for the second order systems. So now first order Lagrangian mechanics. So there the Lagrangian is given by this expression, and non-degeneracy means that this form is non-degenerate. It's obviously closed, so it defines the symplectic structure on N. And now you can see the difference between the second order system and the first order system. In the first order system, the configuration space is the symplectic space. In the second order system, we use the cotangent bundle to define the symplectic structure. But then it's even easier in the first order systems. Basically, we have done all the job before. So again, the space-time is the same as before. So all we have to do is we have to present what is the symplectic manifold corresponding to a pair of points, T1 and T2. So here there is an initial choice. It's the product of these manifolds. The difference with the second order systems is that here it's N itself, because now it's equipped with the symplectic structure. And actually, jumping ahead, I want to say, maybe it's a good time to say now, that this is really the difference between the Chern-Simons theory and the Young-Mills theory. After the reduction with respect to the Hamiltonian, to the gauge group action, Young-Mills theory will become more or less non-degenerate second order system. The Chern-Simons is the first order system. So the only difference between the difference between these examples and Young-Mills and Chern-Simons is that first, these are finite dimensional examples, kind of conceptual difference. And second, these are non-degenerate examples. And both in case of the Young-Mills theory and in case of the Chern-Simons theory, in addition, there is an action of the group, of the Lie group, on these manifolds. And but conceptually, that's the difference. The Young-Mills is second order and the Chern-Simons is the first order. So this is the symplectic space, and then the Lagrangian submanifold is just the same as we had when we discussed the first order system. So it's the pairs of points in N cross N, such that there exists a solution to the Euler-Lagrange equations such that gamma T1 is equal to Q1, gamma T2 is equal to Q2. And then it's a second homework exercise to check that in this setting you have the gluing axiom satisfied. And these manifolds M and MF are exactly the same as in the previous case. In the second order case, you're gluing this manifold M by identifying the boundary points, and the result is T1, T3. Alright, so and it's really late, so let's so I think this is a natural kind of the division line between the finite dimensional cases and infinite dimensional cases. So next time I will start with the Hamiltonian formulation of the nonlinear sigma model and of Gauss theory, and then we have the Hamiltonian formulation of Chern-Simons. And then we'll start path integral quantization. That's the plan. Any questions? Great. So that means that everybody